Welcome back everyone. In the last video we talked about how to design a full order observer to detect the faults in the system. But there's a challenge. In complex systems you can't measure everything directly. This is where reduced order observers come in. They're like compact, efficient detectives using only the most essential information to estimate hidden states and pinpoint faults quickly. In this video, we'll explore how reduced order observers work and why they are becoming an essential tool in modern engineers' fault diagnosis toolbox. Let's do a quick recap. So, as we said in the last session videos, x dot is equals to ax plus bu plus ed times the disturbance signal plus ef times the fault signal, and y of t is equals to cx of t plus du of t plus f d of t plus ff of ft. Let's denote this as first equation and this as the second equation. Let's do a simple transformation where z of t is only a subspace of x of t, and our goal is to have z of t goes to t of x of t. So let's define our new dynamics. Z dot of t is equals to g z of t plus hu of t plus ly of t, and the residual signal as r of t is equal to negative w z of t minus q u of t plus v y of t. Let's denote this as equation number 3 and this as equation number 4. So let us now design the observer. As we said here, we want the z to be equals to tx of t. So we have the error signal to be e of t is equals to tx of t minus z of t, and its dot is equals to e dot of t equals tx dot minus z dot of t. And this is equation number, let's say this is 4 and this is 5. Okay, let us substitute 1 and 3 and 5. Okay, so now e dot of t is equal to t times a x of t plus t times bu of t plus t ed times d of t plus t times f of t minus z dot of t, which is equals to minus gz of t minus hu of t minus ly of t. This is equation number 6. Let us substitute equation number 2 in equation number 6. So substitute 2 and 6. We have e dot of t is equals to t a x of t plus TBU T plus T ED times DT plus EF times F of T minus G Z of T minus HU of T minus L and Y of T was Cx as this, yeah, minus L Cx of T minus L du of T minus L Fd times dt minus L Ff times F of T. And this is equation number 7. Now we want to get rid of this z, so let us substitute. We can rewrite this as z of t equals to x of t minus e of t. So let us substitute 4 in 7. Substituting 4 in 7, we can have e dot of t equals to t ax of t plus tbu of t plus t ed dt g z minus g, substituting the z, so minus g times tx, that's just expanded as well, gt x of t plus g e of t, since it was minus times minus, negative times negative is positive, so plus g of t, and finally minus hu of t minus lc x of t minus l du of t minus l f d dt minus l f f of t. Now let's rearrange the terms to have it in a compact form. So e dot of t is equals to ta, we're done with this x term, and minus gt, we're done also with this term, minus lc, and we're done with all terms in x. Now in new, plus first term is tb, we're done with this one, minus hu of t, minus h, and minus ld, and we're done with terms in u of t, plus terms in d of t, so te of d minus lf d and times d of t, and lastly plus t e f minus l f f times f of t, and we're done with these terms as well. Lastly this one, plus g of t. Now we have this error signal. We want, this is e dot, we want to put some conditions so that the error signal is not affected by our states and by the input. So on this equation we derive 3 important conditions. In our design, the first condition, G, the G matrix, has to be stable. second condition, to avoid the input of the states, we want to design this to be 0. So TA minus GT minus LC is equals to 0. And to avoid as well the effect of the control inputs, we want to design this to be 0 as well. So TB minus H minus LD should be 0 as well. So these are three important conditions that we call them Leuenberger conditions. We will have two more conditions when we start designing the residual signal. Okay, let's continue with it. As we said, R of t is equals to negative W T of t minus Q U of t plus Vy of t. Let's substitute. We want to get rid of z and y. So let's substitute. Let's see y. So we want to substitute 2 and 4. No. And yeah, and 4 here in the residual signal. So substituting 2 and 4. Can add one more page. Substituting 2 and 4, we have R of t equals to negative W times T X of t plus W E of t minus Q U of t. Here we substituted z of t with tx of t minus e of t, and we expanded. That's why it's here it's negative and here it's positive, minus q u of t plus, and y of t was this, so let's substitute it here, plus v c of x of t plus v du of t plus v ed of d of t plus plus vf of d times d of t plus vf of f times f of t. Let's group terms as well. R of t is equals to x of t, so negative wt, done with this one, plus vc times x of t, we're done with that one, plus whatever is, so vd, done with this one, minus q times u of t plus v f d times d of t plus v f f times v f of t. We're done with this one, that one, and of course plus w e of t. As you can see, that the two left conditions from the Leuenberger conditions have to be that we design our observer to derive this to be 0 and this to be 0 as well, so that Our residual signal is not affected by our states nor our inputs. So the two more conditions are, fourth condition is minus Wt plus Vc should be equals to 0. Fifth and last condition, Vd minus Q should be equals to 0 as well. And these are the last two conditions in the Leuenberger conditions. So let's recap quickly with what we wanted to do. We wanted to imagine if we have a complex system with a lot of states, and we want to observe not all of the states but some of them. So we have a transformation matrix to get some of the states, and we call them Z of t, and then we get the new dynamics, which is Z dot of t, and the residual signal as such, and then we start to get the error signal, and we denote it as Tx minus Z of t, and from there, from the error signal, we conclude three main conditions. These matrices should be equals to 0 to remove the effect of the states, and these to be 0 as well to remove the effects of the input, and the G matrix has to be stable so that the error should go eventually to 0. These are three conditions, and the last two conditions are from the residual dynamics, and we designed it as so that these matrices should conclude to 0, and these as well to be 0, and these are the Leuenberger conditions. In the next couple of videos, we will talk about more approaches on how to get the residual signal to detect faults for model-based sense. Yeah, and that's it. Please like and subscribe. Hope you enjoyed the video.